And we should be recording. And I might even be able to keep the recording this time. Okay, well, welcome back to online physics. So today, there's a few enough people here, you probably don't even need to mute yourselves. Let's see, where's my share screen? Share the visualizer. Here's the visualizer, there it is. Okay, so sort of a review and a preview of what we're going to be doing the next today, and then we're going to be moving on to, before we move on to new topics. And so I've been, those of you who've been paying attention to the textbook have noticed I've been bouncing back and forth between chapter 27 and chapter 28. And the reason is because I think that it's too easy to isolate these things. And I also believe strongly in something called spiral learning, which is to say that you, if you go back and review topics multiple times, your strength gets stronger. And that's particularly true in the case of things where there's a skill that you need to keep repeating. And so my goal here is by breaking it up, I come back to the topic more times, and so everybody has more of a chance to learn the right-hand rules and remember how this stuff works. So we're going a little bit slower as a result, but I'm hoping that this means that everybody has a much more solid idea of how this works. And this is something I really want everyone to be able to do, is understand the right-hand rules, which then gives you some intuition about how the fields and forces work. So the story so far, right? So we started with these things, but really underlying it, we've realized that it's these things, is that if you have a charge that's moving through a magnetic field, it feels a force. We have V cross B, so the force in this case would be out of the page. So the force on a moving charge in the magnetic field is that. That means if I have a whole bunch of charges moving in a current, I get a similar effect, that I get IL cross B for a current carrying wire. L cross B is an S, so this is also a force going up because this is really just made of these. So both this and this will want to lift off the page. So that means that if you have a loop of wire, it also is going to feel fields, and it's going to feel them in a different and more interesting way. And that's what that's the first thing I want to talk about today. We've covered this very briefly before. I want to come back and touch this a couple more times. Now, at the same time, chapter 28 is talking about this stuff. So here I have a single charge and it's moving through space, and it turns out that as it's moving through space, it's creating its own magnetic field. So if I looked at this picture, there's actually two fields. There's the external field and there's the field being made by the proton. But a proton can't feel its own field. So it's really best to think of these separately. So if this guy's moving, he's making a field, he's also feeling the field created by other things. We know how big this field is, and to do that, we have to use this terrible Biot-Savart law, which tells us how strong the magnetic field is at some position related to where the charge is. And this equation is not really very helpful. There aren't many real-world situations where this would ever happen, because individual particles have very small charges. It's very rare that you have a giant ball of charge moving through space. So this is actually not a very practical formula. But this is a very practical formula because I can have wires that are carrying current very easily. So if a wire is carrying a charge going this way, it has a magnetic field that's coming out of the page on the top and into the page on the bottom. So putting your thumb along the direction of the wire, your fingers curl around underneath. So that means it's coming above the wire, it's down. Beside the wire, it's into the page. Under the wire, it's away, it's towards the top of the page, and above the wire, it's coming at us. But this also means that I can form this guy into loops. And this is also these are very useful and interesting forms. They aren't the only ones we're going to discuss. We're going to discuss coils at some point, and that's going to be the goal of the next couple of days. But these are very, very useful objects to talk about, because these are the sorts of things to make. In fact, current always runs in loops, right? It's impossible to run a current that isn't in a loop of some kind. You need to complete a circuit in order to make current flow. So these are very important cases that we want to discuss. All right, now we actually know everything we need to know. So we'll talk about this first. And we know everything actually we need to know by just looking at this. And so instead of looking at a round loop, I can just look at a square loop and ask what happens to all the sides in the square loop. We've gone through this activity before. I want to go through it a couple more times today and make sure we can get it right.
So what is that orange dot?
That's the battery.
Oh.
Okay, a couple of D's, some lackluster energy. Everyone's feeling it. Nobody wants to get up early anymore, I know. A couple of G's, a couple of D's. Okay. Calvin, why do you think why do you think there's no net force, no net torque?
Because the top and the bottom are like parallel to the electric field, so they have no force.
Right.
And then the left, the force is going up, and then in the right, the force is going down. So
Right.
they're equal and opposite.
That's true. So there's an equal and opposite force, right? So the forces look like that, right? And so, or rather, not like that. So the force on this side is going to be, let's see. So the current is up. So V cross B is into the page. So on the right-hand side, there's a force that's into the page. And on the left-hand side, there's a force that's out of the page. So the magnetic field is going to be pushing this guy into the page and pulling this guy out of the page. So you're absolutely right. There's no net force, but the forces are in different places. So there's a net torque. So it's going to twist it. So it's going to twist, and it's going to twist so that the left edge is towards you. So the D is the right answer, right? So your thinking is completely clear, but it means that there's that so it doesn't move. It'll spin in place. It'll start twisting, right? Now, at some point, it's going to twist, and it's going to twist until it's here, right? So let's look at that picture. So I'll change the view. Bunch of people unsure. Okay. couple of E's, but G's. 2 G's. Ian is being a ninja. We can only see his eyes. Okay, we got the idea. All right, so the G's seem to have it, right? So that's in fact correct. There's no net forces on this guy. Yeah? So if you look at this, so if you look at the top, V cross B into the page means the top one will feel a force up. The bottom one, V cross B, will feel a force down. The one on the left, the one on the right, the current must be going this way, and so it'll feel a force this way. And the one on the left, the current is moving up, and so it'll feel a force that way.
For the top and the bottom ones, do you, I think, is the current opposite of what you drew is what I'm seeing.
Oh,
Don't
I'm
all the
sorry.
forces
You're
go
right.
in?
You're right. I looked. I saw the arrow wrong. You're absolutely right. The whole thing is. I drew that whole thing backwards. It's that way and that way, that way and that way. You're right. So in this case, it's so V cross B. It's all inwards, isn't it? I totally didn't see the arrow. My eyes are failing me. I don't have very good light in this room. So yeah, you're absolutely. Thank you, Aaron. You're absolutely correct. And I'm stupid. So in this case, they're all going to be tugged inwards. The loop is being tugged inwards, but assuming it's made of rigid wire, that's not going to affect it in any way. So there's no net force, there's no net torque. Nothing is twisting it. There's the two forces on the two sides are always the same. So there's no net thing. And you can imagine now, what if I took this loop? Let's go back to that. I'll come back to that again. So let's just do one more. Now, don't succumb to peer pressure. If you're getting this wrong, I really do want to know. And just because everyone else is answering an answer doesn't mean they're right. We've seen that a couple of times. Everyone answers the wrong way. But you're all right. It's C. That's correct. So this guy, and this guy, right? They give opposite answers. In one case, it twists one way. In the other case, it twists the other way, right? But if the field is straight in or straight out of the page, then it doesn't twist at all, right? And you can convince yourself about the opposite of this one. So if we have all the field running into the page, then we get this picture here that I was wrong. And so if the field is either straight through the loop up or straight through the loop down, then there's no torque. Now this means that basically the loop wants to orient itself a single way. So if I have a magnetic field that's running that way, let's use B for a minute. Let's use B for a minute. Right? And I put a loop of current in it like this. So it's in along the plane out of the page. Right? And we want a current through that thing. All right, so in this case, if the current's going into the page on the top, then it'd be V cross B would be down, V cross B would be down. So this guy is fine. So this guy is no torque. And then let's draw one of the other pictures. So he's rotating him, I would say like, let's see. Thought this out a good thing. Right. this guy will feel a torque. V cross B is down, so this guy's getting pulled this way, this guy's getting pulled this way. Right? And then he'll eventually reach horizontal and he'll keep getting pulled. So this guy will want to rotate around to flip in one direction. So if the field is pointing one way, he'll want to flip around to point one way, and the field is pointing the other way, he'll want to flip around to point the other way. But the other thing we can do, instead of flipping the field, we could, instead of flipping the field, we can flip the current, because that also changes the direction of the torque, right? If I change all of these arrows, then I also change all the forces. So I also change the direction the torque gets flipped. So this is enough to get you to the idea of an electric motor. So this is the basic principle behind an electric motor, is I've got a magnet, so I've got a field being set up here. I've got a north pole here and a south pole here. So there's magnetic field lines running from the north pole to the south pole here and then looping around through the magnet. So there's a magnetic field here to the right. And now I set up a battery here that's going to run a current through this loop and then back out and back to the battery. So the current's running through here, hits this contact. The contact runs the current to here, so you can see the green arrows. So for instance, if we look at this wire over here, the current is running towards us, and the field is pushing to the right, so there'll be a net force up on this wire, and there'll be a net force down on this wire. So if you put this whole thing on a pivot, it will want to rotate. And so this wire will want to move up, and this wire will want to move down. Now at that point, when it rotates and it's parallel to the magnetic field, now it's not feeling any torque anymore. But it's still turning. If we let it go and it's on some nice frictionless gimbals, it'll turn and it'll hit that point and it'll go a little bit too far. Now, if we didn't change anything, what that would mean is then it would start feeling a torque in the opposite direction, so it would wobble back and forth, right? It would be like a simple harmonic oscillator. It would go wobble, 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 exactly like a compass needle would wobble back and forth. But we can do something clever, and that's this thing here called a commutator. Now, a commutator, and there's one of these in your car, by the way. It's what the alternator is in your car. Is what this is this is a set two contacts. So you'll notice that this piece of metal here is connected to this wire, and this piece of metal here is connected to this wire. And this metal piece turns with the coil. But these two things, the black things, are brushes, and they don't. So these are like a paintbrush made of metal, right? So the wire can brush against this round piece. So when this thing turns and it reaches the vertical, this slot and this slot have hit the places where the two commutators are, and so the circuit is broken. But because it's got a little momentum, it swings past that, and now this brush is connected to this contact, and this brush is connected to this contact. And so now you've reversed the flow of the current, and so now the thing feels the opposite torque. So it torques around until it hits to here, and then it flips, and now it keeps torquing. And so it keeps always torquing in the clockwise direction. No matter which orientation this thing is, it's always going to feel a torque in the clockwise direction. It feels maximum torque when it's horizontal like this. It feels minimum torque when it's vertical or upside down. But it's always feeling a torque in the same direction, and so this thing will spin. And this is what drives every electric motor. Yeah.
So we have like this electric snow blower, which had like a motor inside it, and like 1 year, like it just like stopped working. Like when you press trigger, like the motor wouldn't turn at all. So when I dissected it, like I found out that like the brushes were like not touching the commutator, like they were like stuck like inside and not really like rubbing against the commutator.
That's right.
And then
that's one of the failure modes of an electric motor, is that eventually those brushes will wear away or get bent away, and you can often repair that. So there is a brushless type DC motor that works on some different principles, and it's not worth getting into here. Electrical engineers or mechanical engineers will learn all about this later on. But right now we're just dealing with the general principles. So the whole thing in action is, so this movie doesn't really loop nicely, but it does show the whole thing, right? So the current is always running the same way from the battery, but which way it runs around the loop depends on which side of the commutator is touching these brushes on the top and the bottom. So as you change the So it flips around so that so it's just showing the torque. Oh, it's showing both torques. I'm wrong. Right? So the torque is always sideways relative to this magnet. And you flip the sign around when it gets to there. Now, in fact, the torque is small at this point. It's smallest there, it's biggest there. But this gives you the sense, this gives you the idea of how an electric motor works. Now, a real electric motor is actually much more complicated. I don't know if I have any pictures of that up. Oh, here I have a different picture. Let me share. Here's another picture of the same thing. Maybe that might be clearer. Here you can see the torque changing as it moves through its rotation. As it hits the commutator, the torque is actually minimum. Now, what you guys are going to do in lab is something like this, but just slightly different. And the answer is instead of flipping the current, all we'll do is we'll turn off the current halfway around the rotation. So what we do is you take your wire and you take one of the wires and you leave some insulation on one side of it so it doesn't touch on when it's touching one way around, but it does touch when it's touching the other way around. This will become obvious to you how it works when you've got the physical object in front of you, and that's the goal for next week's lab, is that you go through all that. But this is enough to understand the idea of an electric motor. Now, real electric motors are actually, I don't know if I have one here. Real electric motors actually work in slightly more varied ways. They'll have more than just one. Let me see if I can find a good one here. No, I don't have one here. So this is an example of one where there's more than one magnetic field and there's more than one coil. And by arranging things in different patterns, it means that you don't have this place in the cycle where you have very little torque. It means you can keep torquing all the way around. So having 3 things instead of 2 can change things. And here in this case, what we're doing is we're flipping the magnetic fields instead of flipping the coil current. But both of these work. So we now have a way, so now we've made a useful device, right? All of this stupid math we've been doing actually leads to something important for modern world. And motors have been around for a very long time. This is not a new idea. Now, one of the sections that we've kind of skipped a little bit is, or we're going to get back to, is AC current, which is just a current where you just make the current go back and forth instead of only in one direction. And that automatically creates a nice motor. So an AC electric motor is actually less complicated than a DC electric motor. For those of you who understand what I'm talking about. If you didn't get that, don't worry about it. We'll come back to that later. New share, let's go back to my visualizer, which is somewhere. There it is. Okay. So let's just cap that off with one of the questions I asked you guys on the warm-up. So, on the warm-up, I kind of I tried to ask you the question backwards. And of course, one thing that may or may not be obvious to you is that a loop like this, or a loop like this, and a loop like this are going to act more or less the same way, right? Even though these are all at different angles. This one's sort of easier to think about, or I guess I should drop this right here. This one's kind of easier to think about because you can think about the torque on this section of wire and the torque on this section of wire, but of course the same thing happens here. So you can have a loop like this. So in this case, I had a loop line in the XY plane, so that's in the plane of the page, with the current running clockwise. So let me see, clock's going this way. And we're looking down on it. The loop is being torqued. The bottom side is being pushed towards us. So this thing feels a force this way, and this thing feels a force this way. Right? And then these sides aren't getting pushed at all. So the question I asked was, what external field is causing this? And a couple of people answered stuff like this, like mac and cheese. Is this being caused by another current carrying wire, or this is being created by 2 wires or a magnet or something? But I didn't want to know what's creating the field that's making it do this. I just want to know what the field was. And Nerd got this right. This is the field running in the negative y direction. So in this case, the magnetic field will be running this way. So just to draw that again. So if the field is this way, and my loop is like this, with the current running that way. Then on this side, if the current's running down, this doesn't have any effect. This doesn't have any effect. Over here, the current's running left, field is down, so this would be forced towards me. Here, the current is running right, the field is down, so this is a force away from me. So this is in the minus z direction and the plus z direction, which is what we want, right? So in this case, what I have to do is I have to use the right-hand rule backwards. I've told you what the direction of the current is, and I've told you what the direction of the force is, and now you have to figure out which way to bend your hand to get those right. So in the bottom case here, I know that the current is this way, and I know the force was this way. So that means the B field must be in that direction. Okay. So a lot of you were trying to like go too complicated and tell me how to make this field. I just want to know what the field was. So again, this is another case where you guys are sort of not quite understanding which terms I'm using, and you're sort of trying to guess at what I'm trying to get at more than answering the question that's in front of you. Sometimes that makes it overcomplicated, and it's easier question than you think it is. All right. So I'm done with this for the moment. I'm going to come back to this a little bit later once we understand a little bit more about things. But now I want to come back to this. So now this is back to chapter 20. Moving charges make fields. So wires make fields. So loops make fields. And we talked about, and we started on this topic last time, right? And I gave you another warm up on that, right? And so this is the same loop again. I've got a loop, the same loop with a current running clockwise. And now describe what the magnetic field is, right? So if the current's running down there and up there, I put my thumb along the direction, say, of this wire here, but my thumb along the direction of that wire, and that means that right here, I will see a field going into the page, and here it's coming out. And over here, thumb along the wire, I'll feel a field going into the page over here and coming out here. So what I'm seeing, so what I'm getting is a field that's coming out of the loop in the middle and into the page and to the side. And several people answered that way. So quarantined, inside the loop, the magnetic field is into the plane, outside the loop, it's out of the plane. Nerd says it comes into the page in the center loop, loops around, and is coming back out. And that's actually the better picture, is it's going in to the page, around the wire, and looping around. And that picture is really the good one. Do I have a picture of that here? Easy to get at? No, I don't. But to draw that like this, it means that the field is doing that. The current is running around that way. So this is the picture that you can draw sort of in 2 dimensions. So this is the cross-sectional view of this sort of 3-dimensional picture, which you want to keep in your head. Okay, now how we got to this, we're going to backtrack and do a little bit more work, is how we got to this is we were using the Biot-Savart law, right, which is dB is equal to mu naught over 4 pi I dl cross r hat over r squared. Right? And we used this last time. The exercise we did is we took a loop of current, and we added up all the bits of current going around the thing by taking little bits of dl and finding that in the center of the thing they all create the field in the same direction, and so we could do the integral and find that the b in the center was equal to, I have to look this up, mu naught I over 2r, where r is the radius of the circle. So we found that for a loop. Okay. So now here's another question. What if I did this?
Wouldn't it just be adding them all together?
That's
So
right.
4.
Right. So it's just going to be 4 times that. So it'd just be this answer times 4. Exactly. That's it. Or if I have n loops, I would have n mu naught I over 2r, right? Where n is the number of turns, we call it. How many times I wrap around. In fact, this could be the same wire. I could have a wire that I wrap around multiple times. And this is in fact how you're going to make your motor. Is you're going to make multiple turns, and multiple turns will mean that you feel the force multiple times, or in this case, you make the field multiple times. So now this is turning into a more useful device, because now I can make a magnetic field stronger just by wrapping the wire around more times. Now, this isn't for free, because of course, for every time I loop this wire around, I'm increasing the resistance of my coil, which means I'm going to have to put in more voltage in order to create that current, which means I'm putting in more energy. So this isn't coming completely for free, but it's very easy to make as strong a field as I want just by wrapping the wire around more often. So that's actually an important and useful device. Okay, let's see if we can get a little bit trickier. So these are wires carrying currents either around like this or around like this. Both times there are so there's a little battery in it in both. Caleb had an answer right away, and now he's rethinking it. Which is always good. Always come up with a first guess and then think about it again. But yeah. Okay. Some A's and some B's. Yogesh, what do you think it's A? You don't have your mic on.
I just thought like the multiple loops, I just thought it would add up.
Well, they will add up, but here's the question: is which way is the field from this one being made, and which way is the field from this loop being made? So this thing is like a half loop. So if I put my thumb along it, he's going to be creating a field into the page, right? This guy's making a field which way? I'm going to be out of the page, right? If I put my thumb along this one, he's headed to the left, and so my fingers curl up, and so he's making a field that's out of the page. So the inner loop is making a field out of the page, and the outer loop is making a field into the page. Okay, so these two are, so you're right, they add up, but they add up in different directions, and because magnetic field's a vector, I have one going up and one going down. Yes, Jacob, we got it. Right? So it's got to be B. So in this case, right? So those of you who answered B had it correct. In this case, this thing is pointing down, and this thing is also pointing down. If you think about it, this is kind of a distorted loop, right? This is like the loop we had before, but I've sort of changed it. Now here's one interesting thing: is did this section and this section, did they make any magnetic field right? Did they do anything? Yes, maybe, no. Do straight sections, right? No, Aaron, why don't they do anything?
Because they're along the same line, and so I don't.
So it's
At that position, there isn't any force.
Yeah, you're absolutely right. So it's this part right here, right? So this is my little section DL. So let's say I'm looking at this wire here, and this is the place I'm looking at. Then this is my R vector. Is from the place is from here to here. That's R. So DL, oops, I'm sorry. You guys have to tell me when I'm doing stupid shit like that. Okay. So here's the place I want to see. Here's my section of wire, DL, right? And so The R vector is from here to here. So DL and R are in the same direction, and so that means that there's zero, this cross product becomes zero. Sine theta between these two vectors is zero because theta is zero. For the other one, right, so for this one, it's going right back, and so for there, here's my DL, and then here's the place I want to see, and that's my R vector. Sorry. So again, DL and R are anti-parallel, and so it's a sine of 180 degrees, and so this is also zero. So both of these cases don't do anything. So if you're ever looking right at the end of a wire, it means there's no effect. There's no magnetic field in that spot. Now there is a magnetic field here and here. Oops, keep doing this. There's no magnetic field here or here because of this bit of wire. There is a magnetic field like here and here, above and below the wire. That does happen, but not in the middle. Okay, the A's are having it. Let's see. So what's the reasoning here? Let's just somebody else talking. Ian, can you tell me why you think that was?
Like bottom part of the loop goes into the page and the top part goes out of the page, but the bottom part, since it's closer, I figured it'd have like a greater magnitude, so it wouldn't cancel out fully, but only some.
Right, that's exactly it. So this guy creates a field into the page, and because we had this term over here, because the closer you are, the smaller the loop is, the stronger the field you get. So the small loop, the small half loop, gives you more field. Now, in fact, you could do the calculation for how big this is, right? Because there's nothing in this calculation that was too hard. We knew, so if you have half the amount of loop, you can guess that you get half the amount of field, which turns out to be correct if you go and do the integral. Is that if I want to know how much field this part of it creates, I just do this, but I multiply it by 1/2 because I'm only getting a half loop. If I want to know how much this one makes, I do the same thing with a half loop. And then I could add those two together, rather subtract them because they'll be in opposite directions, and I could figure out exactly how big that is. And so this is one of the questions you're going to have in the homework, obviously, is doing this. I think at this point, we basically covered everything up through the end of homework 8. So this will be on homework 9, which I'll get together probably later today. So questions like this are quite common. And the nice thing here is that these are both sort of simple cases. The wire is either always perpendicular and equidistant from the point, or it's creating no field at the point. So it's a useful one. One exercise I think we've given on exams before, if we want to get a tough exam, is asking something about like, what's the magnetic field near this arrangement where I have a current that's running to the right and a current that's running down. How do I find the magnetic field there? Which way is it and how big is it? Are the kind of questions we might answer on a calculus heavy exam. Okay, so I just want to back out now and talk a little bit more generally. So loops create magnetic fields. The loop of current creates a magnetic field. But we know this is happening under the hood because we have particles that are traveling around. So say positive particles traveling this way. Or I could get the same effect from a negative particles going the other way around the loop, is that would have the same effect, right? If I had a current of negative, in fact, that's what we have in wires, is it's actually electrons going the opposite direction to the current, and that creates current. So this creates a current going that way. And this again is going to create the same B field. Now, but here's the thing. If I just have a little particle of charge moving in a circle, the average effect of that thing is going to be the same as a loop of currents. So if I just took a little particle, some ordinary particle, and made it move in a circle, that would be creating magnetic fields just like this. Now, there's an object we all know about that has little electrons moving in circles, right? That's an atom. An atom has got a positively charged nucleus in the center, and electrons that, to a first approximation, are basically moving in circles around that atom. So what that means is that if I have an atom, depending on how many electrons I have and which way they're moving around, it's going to create a magnetic field. So for instance, a hydrogen atom, which has just a single electron, will create a magnetic field. A tiny one is a tiny electron and a tiny little loop, but it's moving pretty fast, so that's something for it. So it is creating a magnetic field. It's creating a magnetic field that looks just like a current loop. So, in other words, these particles that are traveling around in a circle, they make a field that looks like a current loop. But this path diagram and this diagram are actually very, very similar, right? A bar magnet and a loop of current actually have very, very similar patterns. In fact, the pattern of a very, very thin bar magnet, like your little metallic guys, looks a lot like this. That this is about the same picture. Now, so this is the thing. If I had a whole bunch of atoms that all had the electrons moving in the same direction around their protons, then they would all be creating magnetic fields in the same direction, right? And so along this axis, I would expect to see a magnetic field pointing up. And that's what a magnet is. In a magnet, you have a magnet's made of iron. There's a couple of other elements that can actually work the same way, like cobalt and there's magnetite or something. I forget what there is in magnetite. But there's only a few elements that do this. But iron is the most common one, and the one we tend to use a lot, like neodymium and ytterbium or whatever that other one is that make the rare earth magnets are also like this. But these guys have got the very particular case. Now, in an iron, there's actually 56 electrons. So you have a big nucleus, and there's 56 electrons. But here's the thing, is the electrons, when they're moving around, if you have an electron moving clockwise around the atom, you also will tend to have another electron moving counterclockwise around the atom. It's a little more complicated than that, but that's basically how you can think of it, is that these electrons, some of them are going around this way, and some of them are going around this way, and some of them are going around this way, and some are going this way. Right, let's see the way. So like this, like this, like this, right? So you have some going around clockwise and some going around counterclockwise and everything. Iron is interesting because the outer two electrons, the valence electrons, both go in the same direction. So in an iron nucleus, 54 of them are all paired and they're going around different directions. But the outermost two electrons in their lowest energy state will go in the same direction around the nucleus, which means I now have a situation where there's a net magnetic field being created by the iron. That's one important property of iron. The second important property of iron, and this is true of only a very small number of materials, is that if I have several of these guys together, iron tends to like to align itself so that neighboring atoms will align in the same direction. Now that's not always true. In fact, it's very easy to see this for yourself. If you have your little magnets we put in the kit, you can play with these, right? So obviously they want to snap together north to south. That's easy. But if I take two halves of this guy and put them back, stop it, and hold them carefully. If I align them with, so they're north-south, north-south, they actually don't want to go together. So if the north poles are both pointing up, they don't want to go together. But if I turn it around, it'll actually stick this way. So it will come apart. And so this is the case where I've got north, south, south, north. And it turns out most materials are like this. But the way iron atoms pack themselves together, and to understand this, you have to get into crystallography and a whole bunch of other stuff I don't really care about. But it turns out that in iron, these tiny little magnets created by these current loops, they all like to align themselves in the same direction, and that is a lower energy state for them. And so when you have a small lump of iron, it will turn out that the iron atoms will align themselves so they point the same direction as their neighbors. And so that's how you can get a piece of iron or a piece of steel, which is made of iron. How you make it magnetic is you can get all their spins lined up in the same direction, then you have a magnet. And that's what a permanent magnet is. A permanent magnet is a piece of iron where all the spins have been set up to all point in the same direction, right? So that's the whole idea behind, this is called ferromagnetism. Or paramagnetism. And this is the special case where you can have, and it's ferro, because ferro means iron, is the special case where you can have these things line up in this, that they prefer to line up together instead of lining them apart. Anti-paramagnetism is much, much more common. And so most materials that have got this this valence electron tend to cancel each other out. So nearby atoms would align opposite. But iron is weird in that it does this particular thing. So this now explains several things that we've kind of mysteries before, right? One thing was why only iron? So we've got an answer to that question. Another one we could ask was, you know, why iron objects will attract other iron objects, or why steel objects will get attracted to a magnet. And the answer is, in this normal form, it's not a magnet right now. And the reason for that is because although the atoms like to line up in the same direction, in an ordinary piece of iron, it looks like this. There's chunks, and these are still microscopic. So there's like hundreds or thousands of atoms in one of these chunks. I don't know exactly how big they are. And in that chunk, all the atoms are pointing in the same direction. They've got their spins aligned, so they're all curling the same way. And so the magnetic field from all those little atoms point in the same direction. But each one of these little things, these are called magnetic domains. They're all pointing in different directions, and it just depends on how that iron crystal was formed. When that iron cooled down from magma, it was kind of just random which way any little bit of the metal was pointing. And so though it's a magnet, it looks like this. But if I bring a magnetic field close to it, what will happen is that some of these guys will line up in the same direction as the external field, because now there's something wrenching them around. So you'll wrench some of them around, and now they'll mostly point in the same direction. So now this guy has turned into a magnet. And so I can use him to pick up something else that's metal. So he's now a magnet. So now I can touch him to something else. And so now I can hold something else from the end of that magnet. Now this magnet is obviously much weaker. And then when I detach it, these guys tend to snap back to their original positions because he's not really set up right. So how do you make a permanent magnet? To make a permanent magnet, what you need to do is take a piece of iron that looks like this. Oh, but before I get to that, let me explain one other thing. You remember how I showed you the video of the blowtorch on the paper clips, right? So I heated up the paper clips and they detached. So it was happening there. Does anybody guess what was going on when I did that?
The arrows were able to like move around as well, so it was even more random.
That's exactly it. Is heat energy is really kinetic energy. And so these atoms are wiggling, and the hotter you make them, the more they wiggle. And if they're wiggling a lot, they don't line up anymore. They don't want to settle into a pattern. They'll all just point in random directions. In physics terms, we've increased the entropy of the system by increasing the temperature. And so they don't need to line up anymore. They're not in the low energy state. They're bouncing around too much. And so they don't have any alignment anymore. So that's called, I believe that's called the Curie temperature, where that happens and you no longer get the spins lining up in the same direction, and so it stops being magnetic, and the paper clips fall. So now we have an explanation for why that happens. Another way you can do that is you can take a wire, run a current through it, and attach a magnet to it, and then run the current through the wire so hot that the wire gets hot and the magnet falls off because the wire ceases being magnetic when it gets really hot. It's also a reason why you can't run your DC motors too hot; they'll stop working. So this is now explaining like a whole bunch of things about and so we know why copper doesn't work. We know why aluminum doesn't work. We know and now we can know how to make a magnet. So to make a magnet, I take an ordinary piece of metal and I heat it up so it's all pointing in random directions. And then I put another magnet nearby. I make a big, strong field nearby, and so now it's hot, and then I start cooling it down. I cool it down slowly, which is a process called annealing. And when you anneal something, what you're doing is you're letting the crystal settle into its form by cooling it down slowly. These guys will gradually all start aligning with the field, and then when it's cold, now they're locked in place again, and they can't move. And so you can turn from this to this by basically heating this guy up and then slowly cooling him with a magnetic field around him. Most iron created by natural processes was cooled down quite quickly and without a strong external field. Although, if you do look at a piece of metal, it usually does have some residual field that points in the direction it is, and that's actually how we know the Earth's magnetic field has changed over time. You can look at an old piece of rock that cooled down a long time ago, and you can measure its magnetic field. And because the small amounts of iron or other stuff it has in it, it'll be pointing along the direction the Earth's magnetic field at the moment it cooled. So now you know where the Earth's magnetic field was at the time that rock cooled down. And so that's how we actually know that the Earth's magnetic field is flipping from top to bottom over time. I'm going to stop here and ask if there's any questions, because this is all a bunch of stuff I just dumped. This is all crystal clear. Secrets of the universe. Does anyone know how the Earth's magnetic field is created? So we have the Earth, and there's Earth's core. Earth's core is made mostly of iron and nickel. Nickel, yeah. That nickel core is very, very hot, and so this is essentially liquid. The Earth's core is essentially made of liquid. And interestingly, because when the Earth was moving when it cooled down, this ball of liquid is swirling. It's not staying in one place. It's swirling around. And it's also hot enough, this stuff is charged. So because it's so hot, it sheds off its electrons. So you have this big swirling mass of charge. Well, a big swirling mass of charge can make a current loop. And that's what it does, is it's swirling around in one particular way that creates a magnetic field that then we feel on the surface of the Earth. But it's a turbulent, swirling mass of stuff like a tornado, right? It's swirling in one direction. But it turns out that over time, over long periods of time, sometimes that swirling gets very turbulent and disappears, and then actually turns up the other way, swirling in the opposite direction. And so the Earth's magnetic pole flips every, I can't remember, it's like every 100 million years or something, it'll actually change. And not on a regular schedule, it's kind of different. And in fact, right now, the Earth's magnetic field is shifting slightly over time. It moves like, I forget, it's like 100th degree per year or something. It's moving a few miles through Canada as the core changes, right? So one possibility actually that could happen possibly within our lifetimes, although not very likely, is that the Earth's field diminishes in strength a lot. And that would, generally speaking, not be good for us. Because Earth's magnetic field does several jobs of keeping us safe, or one job of keeping us safe. It wouldn't be the end of the world, it wouldn't be a major disaster, but it wouldn't be good for several reasons that we might talk about later. Calvin, I didn't hear what you say. He's just talking, okay.
I was just saying that's great. That's a good thing that's going to happen.
Yeah, it's a good thing. It's another way the world can end. It's so wonderful. what actually happens, so the interesting thing about the Earth, and I should have actually mentioned this before, is so we've got this magnetic field going through the Earth. One thing that happens is we're being constantly bombarded by charged particles from outer space. Are running into the Earth, largely coming from the sun. It's called the solar wind. Is the sun shedding both positive and negative charged particles, and those particles can hit the atmosphere, and most of them hit the atmosphere and they dissipate. But one of the interesting things is that if I have this magnetic field line, what happens to the particles? Remember what particles do in a magnetic field. If there's a magnetic field like this, if I have a particle, it'll want to move in circles. So these incoming particles will move in circles and they'll follow Earth's magnetic field in these little helices. And so you'll have these particles, and it comes up into the South Pole too. They'll spiral, they don't just come in from all directions. They get caught by the Earth's magnetic field and get funneled to the North and South Poles. Does anybody know what this makes? There's something you can see in the sky, but only in the North and South Poles.
Like the Northern Lights, right?
The Northern Lights, the Aurora Borealis.
So are there southern lights too?
There are, yeah. Absolutely. It turns out the southern lights are not as well known because there just aren't many people living in far south of the southern hemisphere. So the northern lights are much more commonly known because there's people living in Canada and UK. I don't think I've ever seen them in Ohio. I've seen them in Canada several times. Once in,
You can see them in northern Wisconsin during the
yeah,
summer.
northern Wisconsin. You can see the best northern lights I ever saw were in northern Wisconsin. Well, it was northern Minnesota actually. Was where I saw the best ones ever. And you have to go look at pictures of this stuff and time-lapse pictures because they're just gorgeous. They look like sheets of light coming down the sky. And it's because of this, which is also because of this. And all of this comes from these two basic principles of moving particles create magnetic fields and moving particles feel magnetic fields. But those two principles generate all of this cool stuff that we have going on in the world. So there's cool stuff about all of this. Magnetism is where things kind of get interesting because it's all sideways. Everything's sideways. So so other things happen. Now, in fact, just to talk about this just one different way to complete the thought that we have. If I think about this current loop, so I have a loop of current, and it creates this magnetic field, right? One way I could think about this is it's actually creating a little north-south magnet, is that this current loop is equivalent to this. And so instead of talking about the current loop as being a loop of current, I could talk about it as being a little magnet. Now, in fact, if you think about this, what this means is if I have a loop of current, it's actually acting like a magnet. So now let's go back to thinking about the electric motor. So let me new share, go back to the motor. So now we can think about what's happening in this picture again. Let's use the size of this picture so you can see a little bit more. So in this picture, now you can think about what's happening with that loop. If we run a current around the loop, so if we run the current around this way, that would mean there's a magnetic field towards us in the middle, which means it's like we're looking at a magnet with the North Pole on our side and the South Pole on the other side. If we run the current the other way, so I run the current this way, that creates a little magnet with the South Pole on our side. So another way of looking at what's going on in this, oh, sorry, you guys have to tell me I'm drawing pictures. I always forget what you can see and what you can't see. Let me go back to the visualizer. So if I have current running this way around the loop, that's making magnetic fields come out of the page towards us, right, by the right-hand rule. That's a little bit like a little magnet with its North Pole facing towards us. And if I reverse the current, so the current's going the other way, then it's like a South Pole pointed towards us. So if we go back to the motor, what the motor is actually doing from another perspective is that what we're actually doing here is we're creating a magnet inside this other magnet. And when it's in this position, so it's when it's in this position, the south pole, the north pole is up and the south is down. And every time we turn it around, we're changing which way the magnet is, which this virtual magnet. So the loop current, the current loop is acting like a magnet where the north pole is attracting south pole and the south the south pole is attracting the north pole. So it's like we're making a little magnet that's flipping around because we keep changing the magnet polarity. So, and we can call this, we actually call this an electromagnet. We're going to get to electromagnets a little bit later, but that's kind of what's going on here. So this entire exercise can be seen as, instead of the wires being pushed by the magnetic field, you can instead think of this as we're creating a magnet inside this, we're creating a second magnet, a littler magnet, and we're flipping the direction of that little magnet. Because it turns out that everything it turns out to be current loops, is the current loops, is that's actually what's going on all the way down. So, completely different way of looking at it. Both ways are valid. In fact, we have some notation for this. If I've got a current loop, I can say the North Pole say is this way, so I'm making magnetic fields pointing this way. I can actually give this thing a name and say, this thing has got, it's like a little magnet, and it's a little magnet of strength mu. And we call that the magnetic dipole moment. You might recall we talked briefly about electric dipoles. That this is an electric dipole, and it has a dipole moment of D times Q, which is how strong it makes magnetic fields. Guess what? These two pictures are identical. If I have a tiny little current loop, it looks just like having a little dipole electric field. So this creates electric fields, like this creates magnetic fields. And so this thing I could say has a dipole moment of P, and I could say this thing has a magnetic dipole moment of mu. So this thing makes electric fields, and this thing makes magnetic fields. Ah, even more parallels between electricity and magnetism. This is kind of neat, right? So now some of these patterns that we saw earlier are starting to make, we can see where they're coming from. So we actually call this little loop of current a magnetic dipole because it looks like a tiny little magnet. It's a tiny little dipolar magnet, two-polar magnet, right? A normal north-south magnet is what this current loop is. This is why, so now this is why we can have magnetic fields even though there are no magnetic monopoles. There's no north and south charges, but we create something that looks like a combination of a north-south charge by making this loop of current. So this is how we get it. Now we can, and that which is like this in electricity. Now there's going to be even more parallels coming, right? We're not at the top of the mountain in the course yet. This is some of the hard stuff. The harder stuff is yet to come, but it turns out there's even more parts to this story. And this is a beautiful, beautiful story once you get all the parts, but there are a lot of parts, so which we're going through slowly. So let's say I had this. You can't answer A. The green screen will eat it. So there's two ways to think about this, right? If this is a little magnet, where's the North Pole? So if we zoom out of this little current loop looks like a little magnet. The little North Pole pointing up. That's the way we're declaring the arrow to point, is towards the north side. So I've got a tiny little magnet here with a North Pole here and a South Pole here. And there's a North Pole here and a South Pole here. Right? What's this guy going to do? Is this guy going to spin, or is he happy where he is? He's happy, right? The North's attracting the South's attracting the North. He's going to stay right there. And he's actually, if neither of these sides is stronger, if that's a constant field, he's actually not going to feel a net force either. He's just going to be happy there. This is exactly the same problem as the one I gave you 60 minutes ago. There's no net force or net torque on that current carrying loop. Is the same question as this.
So for this, like the way I concluded is that if the magnetic field is like going like perpendicular, like straight through the plane of like our loop, that's where there's no net force and torque, right?
There's no net torque, yeah. In fact, there's never a net force. It's because the two sides will always seem the same force. So they'll either be the same force in opposite directions or the same force in opposite directions in the plane. Like they'll always be equal and opposite forces. And so they'll either twist the loop or just pull or push on the loop, but they'll never move the loop because the forces will never be in the same direction on the two sides. So there's actually never a net force on a current loop. There's only net torques. How about this guy? So if the field is being created into the page, the North Pole is facing away from us. That means the current is going around this way. I actually have a little picture here from left over from last time I taught this. So there's a current that's traveling around like this, right? So that means over here, it's feeling the current is down, and that's just along the same as the B field. So this side and this side won't do anything. On the bottom, it's V cross B, B cross B. So if this side feels a force into the page, V cross B, this side will feel a force out of the page. This thing's going to want to flip. Things want to flip like this. It's going to, the downside will feel a force away from us, and the top side will feel a force towards us. This guy's going to flip this way. Or this is a little tiny magnet. This is a little tiny magnet, and the South Pole is facing away from us. Well, there's a South Pole up there. So this guy's going to want to flip this way. Right? It's exactly the same. It's exactly the same kind of problem. But now so these things are actually related to each other. How the thing is making the field and how the thing is feeling the field are in fact two sides of the same phenomenon, which is not obvious at first. You have to actually look at loops to get there. Okay. I'll try to remember to get all.
So are you saying that's just a net torque, or there's also a force on
There's
that?
also a net torque. It's just a net torque in both cases. There's no net force. You can never get a net force you can never get a net force with a constant field. We're going to talk about non-constant fields later. We're going to come back to some slightly more complicated examples as we go on. I'm trying to, like, my whole goal here is to go from easier ideas to harder ideas as we get more and more used to them. That's how we do all of physics. So we try to do all of physics. So, so at this point, we sort of finished chapters 27, 28. There's a few details we haven't gone over. I'll probably skip. We're now getting into chapter 29, which is going to be a little bit like doing Gauss's law. So, get your heads ready for some more abstract math. But it's, but I think at this, but I think most people find this a little bit easier. So we'll talk about Empyrean paths. And so we're starting up on another slope on the mountain here. So I will try to get these slides up online as soon as I can. So if you want to go back and practice, so you should, if you're not feeling totally comfortable with some of these exercises, you want to go back and review these sorts of questions in the textbook and, ask yourself, re-ask yourself these questions so you can get them right. I'll probably post the next homework tonight. I'd like to see homework 8 on Monday. And if you can scan it in with your phone and make a PDF of it to send to me, that would be ideal. Is email okay with everybody, or should I set up a Dropbox? Okay. If you're having problems, if you're having problems, write me a note in Slack and to let me know. Or if you're having, or there's final questions in the homework you haven't gotten, write me on Slack. And sometimes if I'm available, I'll just turn on Zoom and we can talk face to face. So. You're not alone. It feels like you're alone. It feels like you're alone in front of the screen all day, but you can be not alone in front of the screen if you want. I don't know. Everybody have a good weekend. There's no question, you guys. Stop playing with your green screen. Have a good one.